episode of Mr. Avila Physics. Today we're going to talk about momentum. The term linear momentum or momentum is defined as the multiplication of an object's mass times its velocity. So in formula form it would be momentum is equal to mass times velocity. Now, since velocity is a vector, then momentum is also a vector, which means that momentum is going to have both magnitude and direction. The magnitude of the momentum is going to be given by the multiplication of mass times velocity, and the direction of the momentum is the same as the direction of the velocity. Now, the units for momentum are kilograms times meters per second, and there is no special name for this unit, okay? Like joules or newtons or anything like that. So the units for momentum are simply kilograms meters per second. Now, let's talk about some examples of linear momentum. For example, a car that is moving faster will have more momentum than a slow-moving car. A heavy truck will have more momentum than a small car if they're moving at the same speed. So the more momentum that an object has, the more difficult it is to stop it, okay? And the more momentum that an object has, the greater effect it will have on another object. Okay? So if two objects crash or collide, then an object with greater momentum will have more effect on an object with less momentum. For example, a football player is more likely to be hurt if he's tackled by a heavy opponent running fast instead of a skinny opponent running very slow. Okay? A heavy, fast-moving truck can do a lot more damage than a slow-moving motorcycle. So these are examples of momentum, but how does momentum relate to what we've talked about so far? Okay, so since momentum is equal to mass times velocity, in order to change momentum, we can either change the mass or we can change the velocity. And as defined earlier, a change in velocity is acceleration. So in order to change the momentum of the object, we need to cause an acceleration. And in order to cause acceleration, a force is needed. So a force acting on an object will change the momentum of the object. It will either make it go faster, it will make it go slower, or it will change its direction. As a matter of fact, Newton's second law was originally stated in terms of momentum. The original statement for Newton's second law was the rate of change of momentum is equal to the net force applied to it. So in formula form, it said that the force is equal to change in momentum over time. Okay, and let's see how this statement of Newton's second law relates to the statement that we know of, F equals ma. So let's look at this for a second. So Newton said that the rate of change in momentum is equal to the net force applied to it. So net force is equal to change in momentum over time. How do we calculate change in momentum? Well, change in momentum is going to be equal to final momentum minus initial momentum. So this right here, this is final momentum, and this right here, this is initial momentum. So change in momentum is equal to final momentum minus initial momentum, which is this right here. Then from here, we can factor out the mass. And then what do we call this right here? Bf minus Vi. Well, this is simply change in velocity. So we can do this. And what do we call this term right here? Change in velocity over time. Well, as we learned, change in velocity over time is equal to acceleration. So that means that the change in momentum over time can also be expressed as net force equal to ma. However, this original formula is a little bit more precise, right? It's more general because it can take into consideration times when the mass of an object changes. For example, as a rocket goes up into space, it is losing fuel on the way up, so its mass is changing. So this is a more general form of Newton's second law. All right, let's try an example. So for a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second. If the ball has a mass of 0.06 kilograms and it is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough to lift a 60-kilogram person? Pause the video here, take a couple of minutes and see if you can come up with this problem on your own. All right, welcome back. All right, so just now we learned that force is equal to the change in momentum over time. So force is going to be equal to mass times the change in velocity divided by the change in time. So force is going to be equal to mass 0.06 times the change in velocity, right? Final minus initial over time, 4 milliseconds. So that means that force is going to be equal to 0.06 times 55 divided by, that'd be about 825 newtons. Now, is this force enough to lift a 60-kilogram person? Well, I think so. What's the least required force to lift this person? So, mg. So the least force necessary to lift a 60-kilogram person is 60 times 9.8, which is equal to 588 newtons. So the force given to a tennis ball is large enough to lift a 60-kilogram person. And this is how your textbook solves it. So, okay, pretty much the same thing. All right, let's look at this next example. Water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second and is aimed at the side of the car. The side of the car stops it. What is the force exerted by the water on the car? Pause the video here, take a couple of minutes, and see if you can answer this question. All right, welcome back. So once again, here we have that force is equal to change in momentum over time. So force is equal to mass times change in velocity divided by time. So here we have 1.5 kilograms of water moving at 20 meters per second, but the car stops it. So the final velocity becomes 0 and the initial velocity becomes 20. And the time is 1 second because the rate at which the water leaves the hose is 1.5 kilograms per second. So here I can calculate the force. So this will be equal to 1.5 times 20 divided by 1. That gives me a force of negative 30 newtons. Now, this force that we just found, this is the force that the car exerts on the water, which makes sense that it's negative because the car is doing a force in this direction and the water is moving to the right. So if I want to find the force exerted by the water on the car, then the force exerted by the water on the car goes in that direction. So our answer should be positive 30 newtons. Okay, so be very careful when reading a problem and make sure that you answer the question that is asked by the problem. All right, so here's how the problem solves it. Okay, your textbook solves it. All right, now what happens when we have two objects interacting with each other? Okay, say for example, we have two balls moving towards each other, crashing, and then moving away. What happens to the momentum of each ball and what happens to the total momentum of the system? So here we can see that if we just consider our system as the two balls moving towards each other and we ignore the outside forces, then the only force that is happening on the systems is this one and that one. The force that A is applying on B and B is applying on A, which are of equal magnitude but in opposite directions. Okay, so after they collide, then they're going to move away in different directions. So the momentum of each individual ball might change. I mean, it does change because the direction changes. So just with that, the momentum changed. So the momentum of each ball changed, might be different, but the sum of the momentum before they collide and the sum of the momentum after they collide is the same. And that is one of the most important conservation laws in physics, along with conservation of energy. So the law of conservation of momentum states that the total momentum of a system remains constant in the absence of external forces. So this means, another way of saying this is that the total momentum before a collision and the total momentum after a collision are equal. So our formula states that initial momentum of A plus initial momentum of B is equal to final momentum of A plus final momentum of B. Okay? All right. So if we have to be very careful on what we look as our system, like it says here, the total momentum of an isolated system. So a system is what objects are we looking at? So for example, if I have a rock that is falling, then the momentum before the fall and the momentum after the fall is not constant because there's an external force acting on the rock, which is the force of gravity. But if we include the Earth in our system, then our system becomes the rock and the Earth. And then the momentum is conserved because as the rock falls, the Earth actually moves up a little bit. So the total momentum is conserved throughout the path. But the effect that the rock has on the Earth is negligible because of the huge difference in masses. So let's look at this example here. We have a 10,000 kilogram railroad car traveling at a speed of 24 meters per second, strikes an identical car at rest. The cars lock together and move as a single car after the collision. What is the speed after the collision? Pause the video here, take a couple of minutes and see if we can answer this problem. All right, welcome back. So here we have two objects, M1, M1v1. So here we have two objects, M1v1 plus M2v2 is going to be equal to M1v1 prime plus M2v2 prime. This prime symbol means after the collision. So before the collision, the second object was not moving, so it had no momentum. So then I have M1v1 is going to be equal to M1v1 prime plus M2v2 prime. But I know that the two cars are moving together after the collision, so their velocity is the same. So then I'm going to have here m1 plus m2 times v prime. So that means that, okay, I'm going to have here, well, v prime is going to be equal to m1 v1 divided by m1 plus m2. And what do I know about the masses? Well, the cars are identical, so the masses are the same. So then this is going to be equal to 1 over 2 v1. So the velocity after the collision is going to be equal to 12 meters per second, half of the velocity, half of the initial velocity of the car. You don't have to solve this problem just with letters all the time. You can put numbers right away on this step. You can put numbers, and it might be easier for you to solve that way. Here's how your textbook solves it. Okay. All right. Let's look at another example. Calculate the recoil velocity of a 5 kilogram rifle that shoots a 20-gram bullet at a speed of 620 meters per second. Recoil velocity is the velocity of the rifle as it moves backwards after firing. Okay, so here we have our system. What is our system? The rifle and the bullet. So then we're going to have here the total momentum before the collision, which is going to be m1v1 plus m2v2, and that's going to be equal to the total momentum v1 prime plus m2 v2 prime. It's going to be equal to the total momentum after the collision. Now, a collision is not necessarily a crash. A collision could be a crash, could be an object bouncing off a wall, could be a racket hitting a ball, could be an explosion. All of those are examples of collisions. Okay, so here, initially, before shooting, both the rifle and the bullet are not moving. So the total momentum before firing is 0. Now after firing, we're going to have mass 1.020 times velocity 1, 620, is going to be equal, plus the mass 2 of the rifle times the velocity of the rifle after the collision is going to be equal to 0. So solving this, I get that v2 prime is going to be equal to 0.02 times 620 divided by 5 gives me a value of negative 2.48 meters per second. Does it make sense that it is negative? Yes, because the rifle moves in the opposite direction as the bullet after being fired. Okay, so careful when, remember that momentum is a vector quantity, so careful when you have to include the direction when you use the formula of conservation of momentum. Okay, so some of these signs might change to minus depending on the direction in which the object is moving. Okay, so here the rifle will have negative momentum after firing, and the bullet will have positive momentum after firing. So when you add them up, it is 0, which is the same as before firing. See? So, opposite direction. All right. Thank you for watching.